Hello everyone, welcome from my side. I'm Andre Mönike. I'm product manager for Composite technology. Today I'm sharing with you the latest developments on the HyperWorks side with respect to composite technology. Short overview of the agenda. First, I'm going to kind of go through the general composite workflows in a quick overview. And then I'm going to focus on integrated composite stress toolbox enhancements and also the injection molding mapping workflow that's been coming new recently. So let's first look into the different kind of workflows. And the first one is a very classic, so just the normal composite layup solution workflow. And in this one here, you would basically start with the same thing that you could start any other of the workflows with, which is creating your material model. For example, in Multiscale Designer, if you really want the depth and insight that Multiscale offers. And on the other hand, we do have the ply-based modeling capabilities of HyperWorks, which enable you to very quickly create and also modify your models. And for the layup solution, that includes also draping simulation. Combining those two, so the multi-scale design and material model and the draping simulation, you can then work your way through to fully create your model and obviously solve it, for example, with OptiStruct, our structural solver, to go either the linear way, or if you have multi-scale designer, you can not just go the non-linear solution route, but also include progressive damage that Multiscale provides to you. Meaning in the post-processing, you will have access to fiber matrix results with full progressive damage. Now, in comparison to this one, the next workflow, just as an overview, because it has also been a rather recent addition that you might not be aware of, it's the new CPP solution, in which we also combine multi-scale designer, but this time with a partner product, in this case here at an equine, which provides all the structural information in a specific format to us that will lead to higher fidelity models than what has traditionally been done and possible on the winding simulations, which means we're supporting the slices so that for the winding and where the paths are crossing each other, we actually get all that information also into the structural model. And as you can see here on the right side, in this little image already, well, not all the elements have the same values around the circumference, which has been the kind of traditional approach. And of course, that also goes further into the post. So then you would basically see those effects traversing down and being very obvious also on the results side. And last but not least, we got the injection molding workflow, which again can be used together with multi-scale designer, but then starts from an injection molding simulation, which gives you the fiber orientations and temperatures that you can bring over into HyperMesh, and for which we have created a new mapping workflow to make your life easier. And then again, you can go into OptiStruct for solving it and do your post-processing on top. So that just as a first roundup. Now let's continue and concentrate more on the updates themselves. And the first topic here is the integrated composite stress toolbox enhancements. And yeah, the first one, functionality that was added is the element-based analysis, which means if you're used to the composite stress toolbox and used to getting your engineering constants for materials and plies and laminates, you can now do that straight away also from an existing FE model with just selecting the elements. We are supporting currently OptiStruct, Nastran, Abacus with the various property types that you can see there. As a side note, as normally people are looking for the midplane values, that's also what we are providing. So if someone looks at engineering constants of an element, then the midplane values are shown. And also a nice addition is that the drape tables are actually supported, which we'll see if we take a look at the video. So in this case here, I have a drape model, and we can see, if I pause that for a second, that we have areas which actually do see some shear here, 13 degree shear angle. So we should see those effects also in our plies. Let's continue that one here. I'm also reviewing quickly the thickness scaling factor, because that is also something that was enabled just recently. And now we can look at the original calculation, meaning we're doing just the element at the laminate-based analysis. So our laminate has two zones on our head here, and we can see the laminate by plus minus 45, twice 0 minus plus 45. So that's one bit of this complete laminate here, and also the complete one in the second step. Now, when I look at the reserve factor, in this case here, I actually get a 0.7 roughly. Now, just for comparison, and that is actually quite a drastic change, as we'll see now. If I pick actual elements of the structure of our two different zones and do the same analysis, then we'll see, okay, the layup has changed here quite a bit. So, well, 6-degree change in some of the areas. And with the given load that I've defined here, so that's a predefined composite plate load, we can actually see that the reserve factor is basically less than half of what we had before. So there can be significant influence of the draping data towards your results. Yeah, and that was just the first quick feature. Let's go to the next bit. And the next bit is including the thermal properties and also the thermal load and load response. And again, it all starts from the materials. So the engineering constants, obviously, we need to have on our materials. And if the material has the thermal expansion coefficients defined, then we can go through all of the other items and take advantage of that definition. So you can see here on the right, it starts again with just the coefficients themselves, which can be visualized, but it also boils down to available result items. Like in our case, we can then start looking into apparent stresses versus mechanical versus thermal stresses. But actually here it's quite nice, quite easy to see. So if we, for example, look here right in the middle, we can see that if we combine those two values, the residual and the mechanical stress, we'll actually end up here at the apparent one. Okay, so on the thermal properties that I mentioned before. So in this case, we do have two different materials, both fitted with expansion coefficients. And we can see, just as expected, that we can get the thermal expansion coefficients here on our engineering constants for the materials themselves. Again, we can also plot that stuff. And maybe I can just progress forward a bit. Same is true then also for the elements. And if we now do a load response, then things start to get a bit more interesting, because in this case here, I'm actually going to combine our mechanical load with a temperature load, and I'm going to use both or different temperature changes on top and bottom of the laminate. Bearing in mind that this is all then taken a linear, or assuming a linear temperature distribution, because we are not having the conductivity values in our current materials. So now if I run an analysis with the given load, it's actually quite nice to see the effects of the thermal versus the mechanical load. So I'm just selecting all the needed values, and now we can look at the results. this case here, we do see, first of all, our complete load. And then if we scroll down, we can see the different levels. So starting with the apparent stresses, mechanical or residuals, and those ones then can, again, if we look at the table, we can already see, okay, the apparent and mechanical are pretty much in the same range. There's 0.7 difference, and that's actually the one that comes from residuals. But that's usually, again, easier to see if we look at the full thickness plots. So it's easier to grasp. Yeah, being able to compare those would also be a nice addition in the future, but that's not yet on the agenda. Yeah, then let's move on to the post-processing of result files. So normally, up to now, you could only create loads manually in your Composite browser. So you were creating either forces and moments or strains or homogenized stresses. But now for OptiStruct and Nastran, we are reading also the result files and do the post-processing similarly to what the certification framework does for the first by failure calculation. Just in here, we can immediately go to the various elements and do the full thickness plots for the stresses and reserve factors. Again, here important to note that we do everything with the correct offset and also the correct relation between the elemental coordinates in which we read the forces and the material coordinates. But that's easier to also look at from here. So we got a simple model. We are reading some results, and just for the sake of it, I've been checking that the element forces and moments are actually available. So that's why the first plot in here. And now I'm creating an analysis, and I want to do a load response failure analysis, but not on the lambda, rather on the elements, because that is supported right now here. So I'm picking just a few again. And now I have the chance to pick from the existing subcases or simulations. So both of those types are included. So you can pick from whichever are available. And in this case here, I already have a first by failure definition existing, so I'll just use that. Now, if I run this analysis, we can basically see, again, we get our lambda data red in this model. So this is undraped, so it doesn't have any break tables on top. But we can clearly see here, we have our loads in elemental coordinate system. And then we have our loads rotated into the material coordinate system. And also the kind of transformed values for the midplane forces and moments or midplane strains, just so that you know which values you're actually using in the final calculation. Yeah, and then again here we can go through the different items of our different elements, our different subcases, and the actually available results. So very, very straightforward workflow, very easy to get to the values of interest. Okay, and then on the Composite Stress Toolbox, we also have made an addition to support multi-scale designer materials. So if you're running, for example, the CPV or also the injection molding workflow or any other, but you're running your materials straight away from multi-scale designer, you might still want to be able to do some basic calculations on the lambdas, and that is what we have enabled. So now, as you can see straight from here, we have our what I have named the MDS material, so multi-scale designer material. You can check, we get the engineering constants, we get the thermal expansion coefficients. The allowables are not in there, as they are not contained in the result file, and it's nonlinear model, so we are not trying to excerpt any like linear or first by failure values or anything from that. And then just for the case you've never seen how that MDS material actually comes into it, you just create a material with the colored image MDS. And here we go. And you create an assign card, which basically names this and points, go back here for a second, and points to the correct file of your multi-scale materials. So that's pretty straightforward. And then you can go ahead and use it as if it was any other material, except for the allowables. But now you can see here, I can do apply analysis. I'm going to get my apply values. I can go review, as with any other, all my values. I can go do that same thing on the laminate, and it propagates through. And I can also do load response, just the first fly fader is then not available. And obviously the strength quite corresponding cannot be available as well. Yeah, that was the first part on the Composite Stress Toolbox. Now we're looking into the injection molding mapping workflow. And for that one, there is actually a dedicated ribbon. So when you have your HyperWorks 2022.2, you will find the injection molding ribbon available in the view. And you can see how it's split up into the various steps, which we're also going to check out in a short video in a bit. So it's very simple and very straightforward. You really walk through from the left to the right in the process. So that's a very nice addition to work yourself through the process. Now, maybe some things up front if you're not into that topic at all. So when you're looking at the injection molding as a workflow, you would have your molding simulation as one step, and you would have your structural model as another step. So you would have your structural model, and obviously you're getting results from molding simulation here as the fiber orientation tensors, potentially also the temperatures as was outlined in the other slide. And then you need to bring those two together, because very often those are not matching. They're not matching in space, they're not matching in scale. And to make things easier, we've packed that into this new workflow. And then again, you can also add multi-scale materials on top of it and run the whole thing with the new information. And for this one, I got a bit of a longer video because there are a few more steps, and it's actually also a bit of a bigger model. So some steps are taking a few seconds. First thing, you need to enable the injection molding ribbon, but that's very straightforward. You go to view, ribbons, injection molding, and there you go. You have your ribbon available. Then the next step would be importing the molding simulation mesh. And in this case here, we've located our files, and we can see it's actually quite big what's in there, and we're going to be opening it from here so that we get our mold model. Yeah, nothing specific about the settings, so just go to the import. And as I mentioned, this now takes a while, and we'll see in a bit, because if you look here at the number of elements, this is actually a nicely complex and not just too small model. So then we're up to the next bit, which is the fiber orientation tensor results. So basically, we are just again pointing to the correct file and also pointing to the elements for which this file is. So file is loaded. Now we can select the elements, and we're grabbing them here by the component. And after a few seconds, we see that all of them are selected, and we can go continue in our process. So now just hitting proceed. And yeah, in the background now our field entity is actually created, which we can review. So now here we can see there's fields, one which we didn't have before. So points to the file. And there's also a connected table. The third step in the process itself is defining the reference. And for that purpose, we go and yeah, grab ourselves in a distinct area of the model that we can nicely grab in both of the models, both the structural and the modal. So first, again, we grab the elements, in this case here, again, the 4.5 million almost. Now we're looking for the nodes that we want to use as reference nodes. So those should be present in both of the models, not as IDs, but from the positions and how they are connected to the rest. So it's number 1. Number 2, and the last one, number 3. Okay, so now we can again proceed and let the work be done in the background. So the injection molding mesh is then deleted, and we end up with a representation that is a bounding box of the previous model. And with that bounding box, we can then go to grab the structure model. And as we'll see, the structure model is quite different from our mold mesh. So now if everything was aligned already nicely, we would just see our U mesh being in the bounding box and everything would be good. But as we'll see, and that's the general case, that's not very likely to happen. So now we got our structural model here. And if we review the components, we'll basically see that both of them are here. One is just a geometric representation, and the other one is our structure model. Now, if we check the measurements, we'll also see that, well, obviously they're not in the same scale. So one is in meters and the other one is in millimeters. So we gotta do some transformations before mapping. And in this case here, again, we just have to grab the corresponding nodes. So very, very easy, just the 3 nodes. We hit OK, and then everything is set in the background. And with all the information that we have provided, now you can see that we have been moved to the correct place, or to the correct space. And now we can basically go and continue with mapping. So now again, we do have our fiber orientation tensor, which is what we want to use. And then there are some settings on which functions to use for the mapping. But yeah, that's too much level of detail. So it's more important to know that we're doing the mapping in the background, and then we will be able to also review what are the results of the mapping. So if we let this run, we can basically go and also start a review afterwards. Yeah, so now on the left side, we do see our injection molding mesh with the fiber orientation tensor as it was imported for that one. And on the right side, we can see the structural model with the mapped fiber orientation tensor. So just so you know, if we zoom in a little bit, we can also see that there's quite a bit of a different density with respect to the models. And then we can also, for simplicity, check how well the things were basically mapped. So one of the files that's created in the process is kind of a curve that you can compare between the original and the mapped one. So now if we for both of those look at the A11 in the fiber orientation tensor, you can basically see how that affects. And the last bit here is just the OptiStruct example, actually using the whole methodology. And we can see here we have a design card. So we are actually working with MDS material. There's some settings here, but they're not too important at this moment. I'd just like to share is a glimpse at the results as they are calculated in OptiStruct in the end. Let me jump forward to that. Yeah. So now here you would be able to see the matrix equivalent plastic strain versus the fiber strain on the right. You can really see how the various things are kind of, yeah, basically strained. So very nice to look into what's happening there. Yeah, and the last bit that has already been available since the previous version, but something that I want to mention because I think it hasn't been, the word about it hasn't been that widely spread. And that's the Advanced Cure Simulation by Elmat, which is a Altair Partner Alliance company. So with that one, you have the chance to go through a complete and guided process within HyperWorks, also very nicely documented to get to your curing residuals and warpage. And it's really a valuable tool and a nice addition to the capabilities that we can offer. So please take a look at the link here below and get yourself into the details about this workflow. That being said, I'd like to thank you for watching today's webinar, and I hope you got some nice insights in what's currently going on in HyperWorks Composite Solutions. Thank you.